Christy did her PhD work at Johns Hopkins University with Tim Heckman, and then she followed that up with a postdoc at Stewart Observatory and a Hubble Fellowship at Stewart Observatory. Then she had a brief stay at the Max Planck Institute for Astronomy, and then in 2009 she moved to the University of Wisconsin-Madison as faculty, where she is still at. And she's an expert on galaxy evolution, star formation feedback, and galactic scale winds, and so she's going to tell us a bit about that.
All right, thank you. It's been a real pleasure to be here. I've certainly enjoyed my visit so far, and I'm around all day tomorrow, so I'll hopefully get a chance to talk to many more of you. Okay, so you guys, I'm sure, have all heard this a million times. You know, we understand the formation of dark matter halos well. What we don't really understand is how you form, you know, all those baryons within the dark matter halos and all of the complex physics that goes into that problem. And I would argue, you know, of course, there are lots of things we need to worry about if we're trying to simulate this top-down. But I would argue that among all these things, probably the most uncertain ingredient right now is this issue of feedback. You know, all of these present their own problems, but I think this is the one that is arguably one of the most important and still one of the least well understood. Okay, so broadly speaking, feedback refers to the processes by which stars and black holes return energy to their surrounding gas, and that's nicely illustrated by this little star cluster, where you actually, it's the Hubble Space Telescope view, which you really get a strong sense of that star cluster just pushing back against its surrounding gas, probably the gas that it originally formed out of, and thereby, you know, inhibiting any further star formation that might have happened in its vicinity. So why is feedback so important? Well, the, you know, sort of zeroth order statement is that it helps us slow down star formation. Otherwise, we'd see all of it happening at high redshift. This is now a pretty old simulation from way back in 2006, but it was work by Remarkably and his student Ben Oppenheimer. And here I've kind of crammed in the lines to make them more visible. But this is just the observed star formation rate history of the universe. And this is one of their simulations where no feedback has been included. And this is one where feedback has been included. So if you don't have any sort of feedback process, you get way too much star formation happening at high redshift, and that has a bunch of effects on the galaxy population that we observe today. The other real reason that we know it is very important is that if we compare the, you know, some simulation of the dark matter, the number density of dark matter halos, with what we actually observe as far as baryons in galaxies, we might have naively expected that things would just be scaled down, but of course we see these discrepancies at both the dwarf galaxy end and at the giant galaxy end. And for the low mass galaxies, we're pretty sure that it's feedback from star formation that gives us this discrepancy. The high mass end, it's a little bit less clear. Black hole feedback has been invoked, but I think that's a bit of an open question. You also really need feedback to understand why the fraction of baryons is so low in galaxies to begin with. It helps us explain the stellar mass metallicity relation. Of course, we also see that the intergalactic medium is enriched, and we need to get those metals out there somehow. And, you know, again, if you form too many stars at early times, the morphologies of galaxies today are going to be dominated by bulges. And in fact, we see a large fraction of disk galaxies. So you need feedback to disks in the low redshift universe. So I think it's pretty evident to everybody that feedback is really important. The question is, how do we actually put some constraints on it, and how do we actually go about, you know, measuring feedback? One approach that has been kind of commonly taken is to run these large-scale simulations and try out different feedback prescriptions, and then compare them to observations of quantities like the stellar mass and the star formation, or the star formation rate density as a function of redshift. So again, it's that same plot of the star formation rate density, and overlaid are a whole suite of simulations. So this is a very interesting paper if we're just looking at, you know, what various feedback mechanisms do compared to various observed galaxy scaling relations. So this is certainly one approach, and I think it's an approach that you know, is worthwhile, but it's also very indirect, because the probability simulations is there are many possible things you can tune, and it's, I think, a little bit unclear that you necessarily learn something about feedback when you turn one of these knobs and find that something fits. So I think I wouldn't invalidate that approach, but I think it needs to be complemented by some other types of studies. So I think the most direct way of studying feedback is to really look at the kind of most dramatic manifestation of feedback. And these are these large-scale outflows from galaxies that we call galactic winds. And this is a picture that you may have seen many times before, but it's basically our nearest example of a starburst galaxy. This is M82, a very nearby edge on disk galaxy. So in bluish-white here, you're seeing the disk. And in pink, you're seeing some H-alpha emission from this expanding bipolar outflow that we call galactic wind. So how do these things work? Well, there's sort of two mechanisms that people have proposed. This is a kind of cartoon version here from a paper by David Strickland. And the idea behind supernova driving is basically that you have supernova exploding in the centers of galaxies, and you have a lot of these expanding bubbles around star clusters. These bubbles can merge together and form this kind of superbubble of very hot sort of coronal phase gas. This gas is overpressured with respect to the surrounding medium, so it expands until it breaks out of the disk. At that point, it sort of Rayleigh-Taylor fragments, and you get this situation where you have a sort of low-density hot medium with a lot of entrained cooler clouds. And the driving force in kind of this model is that, again, the sort of hot supernova ejecta. More recently, a number of people here, Norm Murray and others, have been working on this idea of radiation pressure driving. The idea that perhaps, much of the power in this outflow can actually come from the impact of these photons from these hot, young, massive stars on dust grains, pushing stuff out. And that's also, as we'll see, probably a very important mechanism in some cases. Just to show you that these winds are truly multi-phase, this is a beautiful picture, again, of M82 taken with the Chandra X-ray Observatory. So you're seeing that in blue. You're seeing dust emission, mid-infrared emission from Spitzer, tracing some cooler dust here. And in the HST image that's showing up here in green shows you the body of this galaxy. You really get the idea that there's a mingling of cooler entrained stuff and then this hot kind of volume filled material. And it turns out that nearly all of the energies and metals are in this hot phase, but a lot of the mass is actually in that cool entrained component. So one of the problems with kind of simulating large-scale galactic winds, and again I'm talking about sort of large-scale cosmological simulations, even simulations that focus on isolated galaxies have some of these problems. The problem is that the particles are simply too big to capture the relevant physics. This is a common problem in simulations. And the supernova occur in dense regions where the cooling time is very short. So in these simulations where you have big particles and you can't separate the gas phases, you see that energy gets radiated away before the bubble can actually expand, because you kind of mix together, since you're averaging over this very large volume, you mix together the cool and the warm phases instead of keeping them separated. And so the common fixes for this are to kind of turn off cooling for a fixed time after stars form, or to actually go in and give your particles little kinetic kicks. But, basically these are sort of sub-grid prescriptions, and it's always a little bit dangerous when you put these prescriptions in when they're not sort of physically motivated by observations. So I think what we need are a lot of observations of galactic winds to help us tune those sub-grid prescriptions, and also hopefully we'll begin to move beyond the sub-grid at some level. So some things that we ultimately would like to know about galactic winds are their geometry, their spatial extent, their velocity, and in particular their mass outflow rates. because that really tells us how these galactic winds are impacting the ability of the galaxies to continue forming stars. And then, of course, we really like to know how the above scale with galaxy mass, star formation rate, environment, and redshift. So my research group at Madison is really busy kind of chipping away at these questions using various different approaches. And ultimately, we are trying to look for these trends across a wide range of galaxy properties. But what I'm going to tell you about today is a little bit more of a sort of focused study on one particular, I think, very sort of zeroth order kind of simple question. And that's the question of whether galactic winds can actually be powerful enough to shut off star formation completely. So this is just a very sort of black and white question that I think is interesting to look at, to ask the most extreme question. Not only can they regulate star formation, but can they actually shut it off? So before diving in, it's worth thinking about how we actually observe galactic winds. And there are basically three ways. One way is that you can go out and you can take images of them, like the images I showed you of M82, to get some sense of how big they are and how much stuff there is in the wind. But that turns out to be really difficult because these outflows are very, very low surface brightness. So there's maybe 20 galaxies where this has been done. But it's not a very effective method outside the low redshift universe. Another way that we like to get constraints on these galaxies is by obtaining spectra of the host galaxy. So in this situation, we'd be looking at the galaxy somewhat like this. And we look for evidence of outflowing gas seen in absorption against the background light of the starburst. And that's primarily the technique that I'm using. The other way that's become very popular recently is to use spectroscopy of background sources. So imagine we had a quasar sitting here, and we took a spectrum of it, and we learned something about the material in the outflow sitting in front of that quasar. And so this is kind of useful for large statistical samples, and they can be useful at constraining the geometry and things like how far this material can get. But so far, those samples are pretty small, and generally always at very large distances from the host galaxy. So good for some questions, but not good for everything we'd like to know.
Can you do it with interacting galaxies and things that are emerging?
Yeah.
I think you'd get a lot of close queries of it.
Well, so Chuck Seidel has done some very interesting work, not with mergers, but with line and break galaxies, where you very often have these kind of foreground-background pairs. And that has been really important in giving us some sense of, how much material you have as a function of radius. And so that's been huge. But you really need, I think in the next generation when we have, 30-meter class telescopes, that'll be really important. But I think for now, the telescope power isn't quite there to do that for large number of sources. And yeah, please jump in with questions. So our kind of current state of the knowledge of galactic winds is that they're sort of ubiquitous in galaxies with high levels of star formation. We don't really know if there's any sort of threshold. We know that in disk galaxies, they have this kind of bipolar geometry with an opening angle of roughly 60 degrees, kind of similar to what you're seeing here in M82. And we know that wind velocities are typically 50 to 500 kilometers per second, comparable to the escape velocity of the host. So it's likely that some of this gas goes out and some of it's probably recycled. And these quasar absorption line studies have shown us that it's possible to get outflowing material out at very large radii from the host out at 100 kiloparsecs. So here in M82 in emission, we're only seeing things out to about 10 kiloparsecs, but imagine this wind extending out a factor of 10 larger. But thus far, mass outflow rates have been very, very poorly constrained, and thus it's been very difficult to really assess the impact that winds have on the host galaxies. And so that's an area where we certainly need to kind of push harder.
Can I ask one? Why is it difficult to determine the mass outflow rate? So you have velocity?
Yeah.
Is it because of the multiple phase?
Well, it's basically because the velocities are easy. So far, all the studies have been done and mostly focused on the cold phase, but that's kind of okay because that's where the mass is. It's really easy to get velocities, but it turns out that usually when you're measuring these absorption lines, all of the common absorption lines are saturated. So it's just really hard to go in and then get column density out. So it's easy to get the velocity, it's just hard to get the column density. And then in cases like M82, you don't really know. You're seeing, because you're looking at an emission process, it has a sort of density squared dependence, and you're only seeing the sort of densest material, so it's harder to make a difference about. And then you have the geometry problems where you don't then know the velocity very well if you're observing it edge.
So is it right to say it's easy for you to get lower limits for mass, but if it saturates, then it might be much higher in mass?
Yeah. So that's really the problem. Most of these lines are saturated.
Is that the only problem? I mean, you get, say, don't you have to do correction factors for like how much sodium is there relative to, and then hydrogen and what's the ionization?
Yeah.
Level population, all those. I mean, is that?
Right, so that's a huge factor too. So the studies have been, so in the optical, there aren't very many good absorption lines. This little dinky sodium line is probably the only one that we can work with, or else calcium HEK. But the problem is the really low ionization potential line. And so your ionization potential corrections are, you have a factor of 10 on certain things. So that's a huge problem. The other problem too is that, when you observe these things in absorption, you don't really know where that material is. If I'm observing this thing full on, and I get some nice absorption line signature, even if I manage to get a column density out, to calculate a mass, I really need to know whether, I'm seeing some big shell at large radii, or whether I'm seeing all that stuff in close to the nucleus. And so you're kind of missing that piece of information too. So yeah, that's a very good point. So coming back to the question I posed, are outflows powerful enough to quench star formation in the host galaxy? Our goal was basically to identify a sample of galaxies that we believed were in the midst of this quenching process, and then kind of figure out what physical processes might be at work, and whether, this wind was part of what quenched the host galaxy. The kind of two problems with that, just observationally, is that quenching is presumably this very short-lived phase, so these objects are going to be rare. And then the kind of second problem is, well, how do you then go in and identify a galaxy that's being quenched and say, okay, this thing is quenching? Luckily, those are both fairly tractable. The solution to problem number one was to rely on the immense database of the Sloan Digital Sky Survey to just look through and call out those few rare, interesting examples of galaxies in this very short-lived phase. The solution to our second problem, how do we find galaxies that are quenching, was to select galaxies based on their spectra. So this is a optical and kind of rest-ray near UV spectrum of a typical starburst, and had I plotted these emission lines at their full scale, they would be kind of wrapping up onto the ceiling here. So in these things, they have very, very strong emission lines. So this is a typical starburst. And here's an example of what we call a post-starburst. And in a post-starburst galaxy, you see immediately the differences. They lack these strong nebular emission lines, and they have stellar features that look a lot like A stars. So basically, imagine forming a whole lot of your stars in a single burst, and then waiting a little while. The massive stars evolve away. You no longer have that ionizing radiation to give you the emission lines, and then the most massive and most luminous stars that are left are the A stars. So you end up with a spectrum that's kind of dominated by A stars. Now, most of the things I'm going to be looking at are not what you would sort of classically call an E+A galaxy. In fact, most of mine would be more consistent with things that are B star dominated, because we've really focused on looking at things in the very earliest stages of quenching. So this one is a little bit older than what makes up most of my sample, but you'll see, I'll show you a fair number of spectra. They look pretty similar. So we selected roughly 130 of these post-starburst galaxies at redshifts greater than about 0.4 from the SDSS1. All of these galaxies, you can see these are their optical images. They're entirely unspectacular. They're just little blue dots. They were, in fact, targeted for spectroscopy as quasars, because that's what their colors said they might be. But it turned out that they were galaxies, so they just got kind of tossed out as mistakes in quasar target selection. This is what a typical Sloan spectrum looks like. To me, this is a gorgeous spectrum. To you, it might look like a bunch of noise. It's pretty low signal to noise, but for me, it's enough to see that we have this blue rising continuum. We have a little bit of a bump. This is where those A-star features are kicking in. But what we don't have are any strong nebular emission lines. To really kind of understand these objects completely, we needed to follow them up with a wide variety of telescopes. We tried to learn about the outflow properties and the galaxy star formation histories from MMT and Keck spectroscopy. We learned about their morphologies from some Hubble Space Telescope imaging. We tried to uncover their AGN content using Chandra, and learned something about any obscured star formation or AGN activity from the WISE infrared observatory. And we're just beginning to accumulate gas measurements for some of these using the year-round plateau observer. So sorry, I know that's a lot of observations, but we'll go through some of these. So for roughly 40 galaxies in the sample, we obtained this high signal-to-noise spectroscopy. You can clearly see these A-star features now. And one of the reasons we were kind of working at this intermediate redshift, I mean, most of the Sloan samples at redshift 0.1, we were pushing all the way out to redshift 0.4 in order to both pick up some of these optical lines and this near UV interstellar medium absorption line called magnesium-2. And this basically helps us learn about the stellar population of the host, and this tells us something about what's going on in the interstellar medium.
Sorry, what is the continuum on the? So those are the hydrogen lines. And then
Yeah, so these are hydrogen Balmer absorption lines. So,
what's the blue continuum?
and so the blue continuum is basically mainly in these sources coming from B stars. And there's very, very few stellar features. Like this is just a noise spike right there. There's almost no stellar features out there. Unfortunately, there is a little bit of stellar magnesium, and I'll show you how we tease that out of our spectrum. But yeah, you get that very, very flat blue continuum from the B stars. So we modeled our galaxy star formation histories in an admittedly fairly crude way. We just assumed a galaxy star formation history that we thought would be consistent with a major merger. So we just, allow galaxy star formation to initially be declining. You get a little boost when the interaction begins, and about a year and a half later, you get this sharp peak when the galaxies actually coalesce. Now we're assuming that all of our galaxies are somewhere on this side of the peak, and we just simulated different kind of exponential decay times for that burst. And so what we're really fitting for in looking at the galaxy star formation histories is the time since that peak star formation and what that decay time has been. And here's an example of some of our spectra. These have a fixed decay time but a different burst age. And you can see that the spectra are evolving pretty rapidly. So these are now simulated stellar population models from Kurzweil and Charlot. And you see the strong evolution both in the nebular content, there's almost no nebular lines by the time you reach here, and in the shape of the stellar population. So again, we derive information about our galaxies by fitting them with these models. So the black is the data and the red is the model fit. And you can see that these fits are generally pretty good, so we have some confidence that we've learned something. Star formation histories are notoriously degenerate, but I think it gives us some idea about what's going on in these bursts. And what we learned from this modeling effort is, sort of what you would intuit from looking at these spectra. We learned that the sort of post-burst ages are actually, pretty young. These are typically 100 million years post-burst, and in some cases, very, very close in time to when the burst happened. They're not heavily attenuated. They have pretty blue spectra generally. That's a selection effect because they were selected as quasars. But they turn out to be very, very massive galaxies. The typical mass is about 10 to the 11 solar masses. So they're maybe good analogs of these that will become elliptical galaxies. The kind of most interesting and surprising thing to us is that when we were fitting for this decay time, almost always, the fit chose a very, very small sort of burst e-folding time, 20 million years. And initially I thought, like, this can't be right, because the crossing time of a large galaxy would be greater than that. So how do you get something to shut off that quickly? But as you'll see later, in hindsight, that makes a little bit of sense, and I think those time scales are kind of corroborated.
Does that come because we don't have the emission lines, but we still have a strong feed?
Yeah, so it's really from that fact that, you know, you can see some of these have a little bit of emission, but that's okay. We weren't trying to get galaxies that were completely off. We were going for ones that were, you know, in the midst of shutting off. And so, yeah, it's just very hard to get continua this blue and not have stronger emission lines than that. Okay, so the really interesting thing from the feedback perspective is the gas kinematics. But as I mentioned, we couldn't just ignore the fact that there could be some stellar contribution to the magnesium-2 line. So looking at our spectra, this little feature out here is magnesium-2, and I've just blown it up over here. And magnesium-2 is a doublet transition, and this is where you'd expect the kind of zero velocity of the lines to be. And you can see that in this particular galaxy, you see a nice magnesium-2 absorption line, but all of that absorption really turns out to be stellar. So in about a third of our cases, while we do see this magnesium absorption, it looks like it's mainly stellar. In the other 2/3, we see magnesium absorption that is both much stronger than the stellar feature and highly blue shifted. So again, the blue lines show where you'd expect zero velocity absorption. And you can see that these are highly blue shifted, and these are the velocities in kilometers per second. And in case anybody likes galaxy spectra, this is just to show you we have a bunch more. In some cases, we do see some zero velocity absorption, but it's also common to see, you know, very little zero velocity component. You can have the bulk of it be outflowing quickly. And here, when I'm quoting the velocity, I'm always quoting the velocity of the largest outflowing component. So here we have a little doublet component out there. Okay, so how do these outflow velocities in the post-starburst compare to other starbursts? Well, we were kind of shocked when we did this comparison. So this is just a plot of B-band luminosity to give you some idea of what the host galaxy is doing versus outflow velocity in kilometers per second. And these are just a number of samples drawn from the literature. The blue points are local starbursting dwarf galaxies like M82. The purple points are a sample of LURBs and ULURBs observed by David Rupke and Crystal Martin. And the only galaxies that are kind of comparable in terms of their luminosity to our sample are the sample of line and break galaxies from Max Technique. And then these red points here are post-starburst galaxies. And notably, there's very, very little overlap. Almost all of the sort of normal star-forming galaxies that have been looked at previously have velocities that are less than about 500 kilometers per second. Whereas we're seeing velocities, you know, anywhere from 500–600 all the way up to 2,500. And those velocities are the velocity at line center. In many cases, we have some TAC spectroscopy that allows us to look at this in more detail. And again, magnesium-2 is annoyingly a doublet. So we put the velocity for this redmost component down here, and the velocity for the bluewards component up here. But if you look at this velocity, in some cases we see material moving out at velocities of 3,000 kilometers per second. You know, 2,000 kilometers per second, and we still haven't hit the continuum level. You know, 1,500, 1,000. So these are really pretty powerful outflows. And the question then becomes, you know, are these outflows really the agents of star formation and quenching? Okay, so to build up our more complete picture of these galaxies, we applied for Hubble Space Telescope imaging. We got imaging of 29 of the sample. And these are pretty awful looking for Hubble images. We were shocked. We were expecting all this great morphological information. It should be a piece of cake for HST to do this at redshift 0.4. But what we found was that most of the galaxies looked effectively like point sources at HST resolution with a little bit of surrounding fluff. This is one that you can see is clearly an ongoing merger. You see some nice tidal tails here. And in fact, nearly all of these if you go in and subtract out that point source, reveal some amount of sort of tidal interaction features indicative of some kind of major merging event. The other thing that was uniform across the sample, so in almost all cases we see some tidal fluff, and a few they're just totally unresolved and you don't see anything. But they turn out to have extraordinarily compact effective radii. If we do a sort of single component model fit to these galaxies, their effective radii are 10 to 200 parsecs. So just incredibly, incredibly small. So to put these in context for you, this is just a plot of the mass of a galaxy versus its size, its effective radius. This is the relationship that we see for early type galaxies at redshift 0. And we put on here a couple comparison samples. So our post-starbursts here are the black points. And these, because they're gas-rich mergers, you might expect them to have slightly different properties than your average elliptical galaxy. So here's a sample of gas-rich mergers from about redshift 0.3. And these red points are some very, very compact quiescent elliptical galaxies that were discovered by Peter van Dokkum and others at redshift 2.5. And you can see that our galaxies are, by and large, have much lower, or have much smaller effective radii for their mass than other samples of galaxies, both local galaxies and these gas-rich mergers at slightly higher redshift. And they're comparable to this Van Dokkum sample, these compact ellipticals that made a lot of waves in the literature, and in some cases even much more extreme. So they're arguably among the most compact galaxies in the universe. Now, one of the things you might wonder is, given how compact their optical sizes were, well, could this just be the fact that we're seeing an AGN in these things? Could the compactness just be that we're seeing some AGN point source? In fact, the galaxies are massive, so they're very likely to have massive black holes. They're the relics of gas-rich mergers. Gas-rich mergers trigger AGN activity, so again, it seems like they would be AGN. But in most of the sample, we don't see broad emission lines characteristic of an unobscured AGN. In a few cases we do. Here's an example. And we can fit this with a combination of a quasar template. You can see this broad magnesium to emission line coming from the quasar with some superimposed absorption. So it's about 50% quasar, 50% host galaxy. But there's really just 2 galaxies in our sample that would fall into this category. So in most cases, we don't see any evidence of an unobscured AGN. We have Chandra imaging of the galaxies that we thought were most likely to be AGN. And again, these were nearly all non-detections. So it doesn't seem like AGN are dominant in these galaxies. They're certainly present, but probably not extremely luminous. Now, to our surprise, again, we're looking at this sample of post-starbursts. We theorized that star formation was mostly over in these things. It turned out that 25 of the 29 galaxies in our Hubble sample were detected at 22 microns with the WISE all-sky infrared survey. And this corresponds to about 12 microns in the rest frame, which is not ideal for estimating star formation rates, but it's okay. And we can do it with, uncertainties of about plus or minus 0.3 dex. So this is just some of the, UV to optical SEVs. This shows you a template that would be appropriate for a quasar, really just a power law. And these are a couple of different possible galaxy templates. Again, we think we can rule out a strong quasar contribution to the infrared based on the fact that these don't fit very well. But what we do determine from these UV to infrared SEVs is that the galaxies still are forming a substantial number of stars, or at least they could be, upwards of 50 solar masses per year for about half the sample. That was a little bit of a shock to us. But then we had to ask, how do we get these kind of blue SEVs with weak nebular lines? And it turns out that, H beta is a factor of 10 to 20 times weaker than we would expect based on the measured dust attenuation from this long wavelength SED that we have. And so we're forced to conclude that either we have really strong differential attenuation, meaning that the stars producing the Balmer emission are attenuated 5 to 7 times more than the stars producing this light. And that seems a little bit unusual because, again, you look at this is B star light. This is not A star light even. So it's saying that somehow your very, very young stars are heavily obscured, but things that are just a few 100 million years older are not heavily obscured. So that seems a little unlikely. We could have leakage or absorption of Lyman continuum photons, maybe matter-bounded H2 regions. But again, this is all a little bit hand-wavy. What seems a lot more likely to me is that what we're looking at are very, very recently quenched starbursts. And in this case, both, the blue rising continuum is indicative of B stars, and all that infrared emission could actually be powered by B stars rather than O and B stars. So I think it's the case that the star formation rates we infer for these things from the infrared probably are indicative of the star formation, in the past, 10 to 100 million years ago, not the star formation rate today. So we're seeing a little bit of that hangover in the infrared. But if we just take the star formation rates at face value and say, okay, well, let's see how these, star formation rate surface densities compare to other galaxies in the universe, we find that they're, in fact, extraordinarily extreme. So again, what I'm showing here is mass on the x-axis, and now the y-axis is the star formation per unit area, so the star formation surface density. The contours here just show, again, this is a sample of star-forming galaxies at redshift of 1, so it's not a perfect match in redshift, but it's not too far off. The black points are post-starbursts, and then this is a sample of gas-rich mergers that we showed you before at redshift 0.3. So you can see there's some overlap with this merger sample, but some of our galaxies are reaching some of the highest star formation rates per unit area that are theoretically predicted. And in fact, there have been a couple different suggestions. Tim Heckman kind of suggested a threshold of 0.1 solar masses per year per kiloparsec squared as a threshold for driving an outflow. And clearly all of our galaxies are above that. Gerhard Muir theorized a sort of limit for how high your star formation surface density could be. Our galaxies mostly exceed that limit. And in fact, a few of them are comparable to the Eddington limit derived from radiation pressure on dust rings. A few of our most extreme examples.
That's assuming what the capacity?
So we're assuming, I have to go back and look at, so Jim Beach just put out a paper on this, and I have to check what he's assuming.
This is based on Norman Todd's model,
Yeah.
right?
Mm-hmm. Yeah.
What they call it.
Right.
It's not
Right.
exactly.
So one question we of course wondered was, could we account for these anomalously high, do we need to account for these anomalously high outflow velocities with a boost from a black hole? Was that necessary to get these very high outflow velocities, given how very distinct they were from velocities commonly seen in your typical starbursts? But I think what we came to realize, and this is some nice work by Alex Diamond-Stanek, is that, these velocities are very, very different than what we see down here. But what's also very, very different is the fact that these galaxies are kind of hyper-compact. And Norm and other people have showed that starbursts generally launch outflows at the escape velocity. And since our galaxies have very, very small radii, we would expect them to have very large escape velocities. And so it's, these are sort of some typical galaxies or typical numbers for our sample. If this idea holds that these outflows are launched at escape velocity, then that's sort of consistent with the numbers that we're measuring. So the sort of Occam's razor argument would be that star formation appears to be sufficient to power the outflows. Although we can't, completely rule out any contribution from an active galaxy.
How do these compare to something like RP20?
So in terms of star formation, they're probably about comparable.
It's just bigger.
Yeah, ARC-20 is more spatially extended.
Like a factor of.
That's a good question. I should go back and look at ARC-220. But I feel like either by a factor of a few to 10. All of the local ULERTs are a lot bigger, and I think that has to do with the fact that local ULERTs have turned a lot more of their gas into stars already, and so you get a lot less dissipation when you merge them than you do in these cases where you merge them something very, very gas rich. And so I think that's the big difference from local ULERTs, because local ULERTs are in the sample.
That's a question about, so you really have high velocity, so that presumably is also the opposite velocity of the star. When did you see the magnesium-2 having a huge drop with?
Yeah, so that's an interesting question. Like, why don't we see higher higher velocity dispersions in the stars? Because so it's hard to measure the velocity dispersions in part because we have these very strong A star and B star features, which these A star features have an intrinsic broadening to them. So it's very, very hard to measure velocity dispersions.
So 2,000 kilometers are typical for many superstars?
Shouldn't be, those extreme velocities I think we can rule out.
Yeah.
I think saying whether it's, 100 or 500 is harder, but I think you can rule out 1,000 pretty easily.
Yeah.
So that is something we have puzzled about. And, it may be that this stuff just isn't variabilized yet. I don't
It's not quite consistent with the outflow velocity.
Yeah, it's hard to think about what would be wrong with our HST measurement. Our masses are pretty solid. It's just not that hard to get a stellar mass for these things. Even if you vary the mass-to-light ratios by a factor of a few, you're going to still turn out to be massive galaxies. And then it's hard to figure out where our HST observations would be going wrong, other than the fact that, you could have the starburst being a lot more compact than the, mass-dominant stars in the galaxy.
So the mass is still dominated by the starburst part.
Yeah, that's the thing. I think these things probably formed roughly 50% of their stars in the burst, which is pretty unusual. Like ULERTs, it's more like 10%. So a substantial fraction of the mass has to come from, the stars that were formed in the burst. And, we have played around with getting better velocity dispersions for these things, and we can't constrain them well, but I think we can definitely rule out 1,000 kilometers per second. So it is a remaining mystery. So we don't have a great way to discriminate radiation pressure versus supernova driving of these outflows. However, I think one thing that's kind of interesting about the sample, and again, fairly different from what is typically seen in local ULERTs, is that the covering factors of the gas are very, very high. And so by covering factor, I mean, what fraction of the starburst has gas in front of it from the outflow. And you can deduce the covering factor very straightforwardly by looking at, unity covering factor would imply that these lines would be sort of black at line center, because there would be no flux coming out. And for many of these, we're black or we're fairly close to being black. So I think, and that was something that was a bit surprising to us, again, because it's not a common feature of outflows and starbursts. And so this sort of tells us that we have a wind that doesn't have holes in it. It's almost uniformly covering the starburst. And that isn't so hard because our starbursts are very compact. But I think these are the conditions under which radiation pressure driving should be very, very effective. You're not getting photons out. They all have to hit the wind. So I think that's a hint that this is possibly, the more realistic mechanism to dominate. Okay, so I want to kind of summarize what we learned about these, and then just quickly talk about kind of one case study that I think is kind of intriguing because it's one of our more extreme examples. So we saw that all of these galaxies had type tails indicative of late-stage mergers. They have very, very compact morphologies, probably indicating they're the product of a very dissipational, very gas-rich merger. The AGN activity in these things is present but very weak. They have very, fairly high infrared-based star formation rates. In some cases as high as 500 solar masses a year. They all have these absorption lines indicative of outflows. Well, not all of them, about 2/3, but this is probably just a geometrical argument. In some cases, you may be seeing this edge on. And again, these velocities were, sort of 2 to 5 times higher than we commonly saw in massive starbursts. And, we make arguments that these compact outflows, or these outflows are probably driven by a compact starburst rather than a AGN.
Have you had any handle on the you can estimate, I know it's uncertain, but the total mass loss rate of these things?
Yeah, so that's what I'm going to show you for this one galaxy where we can do it. Okay, so this is just one of our poster child galaxies, and it's probably the most extreme one in our sample. It's at a redshift of about 0.6. Again, high stellar mass, 10 to the 11. Post-burst age for this is among the youngest in our sample. So the age I would derive from my fitting would be about 10 million years post-burst. It's also one of the more compact galaxies. It has an effective radius of 135 parsecs, so really freakishly compact. This is the HST image. Again, most of the light is in the core, but there is some extended diffuse envelope, suggestive of some kind of merging activity. We do detect this source with Chandra, but it's a core count detection. We can look at its ratio of O3 to X-ray fluxes, and that gives us some idea about how heavily obscured it is. So probably of order a factor of 10. We can use this corrected X-ray luminosity to predict its mid-infrared luminosity, and it turns out to be about 400 times less than what we observe in the mid-infrared, indicating that what we observe is likely dominated by star formation. So even if we said this thing was 100 times obscured, we would still find that most of our light would come out from the starburst. And the infrared, assumed infrared-based star formation rates range from about 350 to 1,400 solar masses per year, depending on the kind of templates you adopt or whatever. So this implies very, very high star formation surface densities, again, kind of comparable to this Eddington. So this is the one galaxy right now for which we have CO observations, and I'm not an expert on this stuff, so I would refer you to Jim Beach's paper. But he's able to use the CO detections to calculate a mass of molecular hydrogen of about 2 times 10 to the 10. And in this case, we think that almost all of the gas is basically participating in star formation. So basically all of the gas would be in the molecular phase and available for forming stars. Jim has found that when you compare the infrared luminosity of this source, again, we're assuming that most of that is star formation, versus the measured CO luminosity, it gives you one of the highest values. And this band here is what he computes as the Eddington limit with these assumptions. It's hard to read here, but his opacity within that plot, it looks like 5 to 30 centimeters squared per London. Don't look at the paper.
15 to 30 centimeters squared.
Yeah, per gram.
Which is about as high as you can possibly get velocity.
Yeah. So again, he thinks it's basically kind of turning all of its available gas into stars at a rate that's very close to this Eddington limit. The outflows in this source are about, the sort of mean outflow velocities around 1,400 kilometers per second. There are components of the outflow all the way out at 2,000 kilometers per second. And the really cool thing about this source, which I only realized recently, is that when you look at these magnesium 2 lines, we have this doublet. And the doublet ratio tells you about how saturated the lines are. And it turns out that in this particular case, the lines are not saturated, which I'm still trying to figure out why that might be the case. But since they're not saturated, it's pretty straightforward to get a magnesium column density with a few extra assumptions about dust depletion and metallicity, you can turn that into hydrogen column density. And again, factors of probably 3 or 4 uncertainty there. The outflow mass, if you do that, involves some additional assumptions about geometry. So again, I would say this is probably a lot more uncertain. But if we just take sort of some of our best approximations for these quantities, we would find that about 4 times 10 to the 9 solar masses exist in the outflow. And the mass outflow rate would be about 400 solar masses a year, which is comparable to the star formation rate of this galaxy. So from that, we can say, okay, well, we know how much gas we had. We had this 2 times 10 to the 10 solar masses of H2. If we look at how much gas is flowing out, we can figure out how long it would take for outflows to quench the starburst. And that quenching time would turn out to be about 50 million years. However, that's kind of ignoring the fact that you also have gas being turned into stars, so if this thing keeps forming stars at its current rate, the quenching time comes down to about 10 to 25 million years. So for this galaxy, we are, I think, very clearly witnessing it in the kind of very, very last stages of the assembly of a massive stellar bulge. I think this must be in a very intense and incredibly short-lived phase, and we're kind of, just seeing this quenching process in action. Now, I think it's interesting that the most massive galaxies in the universe, if we analyze their stellar populations today, appear to have formed their stars in very, very short bursts at high redshift. This is a really nice figure from Daniel Thomas. Just showing you kind of schematically, this is look-back time, and these are galaxies with different dynamical masses, so just divide by 10 to convert to stellar. So our galaxies are kind of comparable in mass to these guys. Most galaxies of this mass formed their stars long ago. We're looking at some kind of rare late-forming examples. But they form their stars in these very, very short-lived bursts. So I think the galaxies that we're seeing are probably good analogs for these high redshift elliptical galaxies. So kind of coming back to my initial question, can galactic winds quench star formation? I would say yes, sometimes. I think in normal star-forming galaxies, they certainly don't, but they probably do play an important regulatory role. In very, very compact starbursts that result from these highly dissipational galaxy mergers, I think the resulting star formation surface densities are probably limited by radiation pressure feedback. It seems plausible. So feedback is limiting their star formation, but the outflow is also just sort of as important as the star formation rate in using up and expelling that gas and ultimately quenching the burst. So I would say that gas exhaustion and gas from star formation and gas exhaustion from driving stuff out probably play roughly equal roles. So I think the bottom line is that feedback is extremely important in understanding the formation of very massive early types at high redshift that evolve into the ellipticals that we see today. So I'll leave it at that.
Time for questions.
It's not a naive question, but so you have these galaxies that quench their star formation. Does the star formation then resurface again?
Yeah, I don't know. I mean, it's hard to map forward in time. I mean, I think for many of these ellipticals that formed at high redshift, it's not unlikely that they later merge with something else and get some rejuvenation of star formation that builds up the galaxy's size, because we don't see things today that are as compact as we see at high redshift. These things, because they're redshift 0.6 to redshift 0.4, don't have a lot of time to have subsequent mergers, and they could also reaccrete gas from the IGM. You don't have a ton of time to do that. So I think the answer is there are not very many, these things are rare at high redshift, and so the space density of their low redshift counterparts is going to be very low, and that's probably why we don't see too many things.
So on their own, they've completely merged.
Well, these guys, probably won't, just because they're not at super high redshift. I think the ones at redshift 2.5 have plenty of time to go through more cycles.
So I was wondering if you could see like, two of these outflows. It's
Oh,
famous,
yeah.
But I guess.
Well,
yeah,
what you do see in most of these, when you look at the line profiles, are several distinct components. And that may very well be indicative, mergers are messy things. And so usually something happens at first passage, and then you get a big burst at coalescence. And those discrete sort of shells that you see may very well be tied to kind of spikes in star formation rate. But our population synthesis isn't good enough to disentangle things at that final level.
When do you expect these things to turn in?
Yeah, well, there are in the local universe some very compact galaxies that have been formed. And so I think, I haven't checked the space densities. It's unfortunately hard to get a space density for these because they were targeted by Sloan in such a weird way. But I think the space density has got to be extremely low. I mean, I'm sure Sloan isn't finding all of them, but in 10,000 square degrees, there are order, 150 of these. So it's very low. So I think locally, we just don't expect to see very many. So I think they would be, presumably compact ellipticals were they to evolve anyway.
When you say you try to show massive outflow and quench star formation, and then you also comment about that there's actually star formation going on. And so half the gas got driven out, half the gas got turned into stars. Is that counted as quenching star formation because they just have the two change in star formation rate?
I was surprised it wasn't larger. The only thing is that we don't, at some level, those things have to be linked because what's driving the outflow is the star formation. So I guess, I was a little surprised that number wasn't larger, but I think they are kind of causally connected in that way. It's actually, so again, people have had tons of trouble getting mass outflow rates. But the numbers that people have come up with, again with kind of factor of 10 uncertainties, generally are comparable to the star formation rate. They're almost always within the factor of a few of the star formation rate. So I think that's pretty consistent.
So equivalent if I ask, when you do the modeling about star formation history, what's the peak rate of star formation?
Yeah, so that's something that it's again hard to, so I've just assumed a model where I think the peak is at 100 solar masses a year, but that would of course be adjusted based on the total mass in my galaxy. But it's something that, it depends a lot on how quickly you form those stars. If you form them all in 10 million years, you'd have an incredibly high peak. If you spread that out over 500 million years, it would of course be much lower. And the modeling isn't good enough to distinguish between those two scenarios, presuming that happens, a few hundred million years in the past, or even 10 or 20 million years in the past. We're just not sensitive to telling us, what the peak was. So it's hard to say. Again, using the burst model that I assumed, it's of order 100 solar masses a year.
Comparable to the day.
Yeah, so kind of Euler play. I guess they're, but again, this would all get scaled based on the total mass of the galaxy. So, something like Euler.
One more question. So is the star formation efficiency in this particular source consistent with lower redshift? It seems like it's higher, actually.
Yeah, well, so I think it's sort of consistent. Like Jim Beach's stuff is really saying that, in a normal galaxy you have pockets of gas that are forming stars embedded in large quantities of gas that aren't.
Depends on if you scale up molecular gas.
Yeah, and so basically this is like saying the whole galaxy is molecular gas and it's all turning into stars. So the star formation efficiency would be much higher than a typical disk.
Well, if we have more questions for Christy, we can ask over cookies, although I'll be taking her to the Galaxy discussion, so if you want to ask them, ask quickly. She'll also be here tomorrow, and we're going to take her to dinner.